We now turn to the definition of thermodynamic equilibrium, a core concept of thermodynamics. Thermodynamic equilibrium implies two primary conditions. First, there are no macroscopic flows of matter and energy within the system. And second, there are no macroscopic flows of matter and energy across the boundaries separating the system from its surroundings. When multiple systems, each with potentially different properties, come into contact, they are deemed to be in equilibrium if the macroscopic flows between them cease. In essence, a system or systems are in equilibrium when nothing is moving or changing. Thermodynamic equilibrium can be dissected into three specific equilibriums. Thermal equilibrium. This is characterized by the absence of heat flows between the system and its surroundings, ensuring a uniform temperature throughout. Mechanical equilibrium. In the context of multiple interconnected systems or subsystems, no system exerts macroscopic work on another, which means there is no macroscopic motion. Chemical equilibrium stands as a significant component of thermodynamic equilibrium, especially for open systems. It emerges when there are no flows of matter either within the system or between different systems. While classical thermodynamics might primarily define chemical equilibrium by the lack of matter flows, it is essential to recognize that chemical equilibrium also includes the absence of chemical reactions or phase transitions. Simply put, if there is no physical movement or chemical reaction of matter, the system is in equilibrium. Let us first consider the concept of mechanical equilibrium using a system of gases as an illustrative example. Imagine two subsystems, one with a pressure of P1 and the other with a pressure of P2. They are separated by a freely moving piston. The entire system is isolated from any external influence. How can we determine when the system achieves mechanical equilibrium? The answer lies in the pressure of the two subsystems. Equilibrium is established when there is no difference in pressure between them. This pressure differential acts as the driving force, pushing the system toward mechanical equilibrium. But the actual balancing act is realized through the movement of the piston. Once the pressure in both subsystems equalizes, the piston stops moving, signifying that mechanical equilibrium has been reached. Please remember this example. It provides a foundational reference for understanding the general principles of equilibrium. And now, what about thermal equilibrium? We have a similar setup, but now we are dealing with a hotter subsystem and a colder subsystem, which can, of course, exchange heat. So, when is thermal equilibrium achieved in such a system? Thermal equilibrium is established through the flow of heat. This means that heat flows from the hotter subsystem to the colder subsystem, analogous to mechanical equilibrium. There exists a parameter that determines the direction of the heat flow and governs this approach to the equilibrium. And when there is no difference in this parameter between the subsystems, then they are in thermal equilibrium. This parameter is, of course, temperature. So, just as pressure is the driving force establishing a mechanical equilibrium, temperature is the parameter establishing a thermal equilibrium. Let's take a closer look at the concept of temperature, which is crucial for thermodynamics. Temperature is formally a property that determines the direction of energy flow as heat when two systems come into contact. By our definition, heat flows from a system with a higher temperature to one with a lower temperature. Analogous to the movement of a piston due to pressure differences, when two systems come into contact, heat will flow until the temperatures of both systems are equal. Once the temperature of both systems are the same, we say they have reached thermal equilibrium. Related to the concepts of thermal equilibrium and temperature is the so-called zeroth law of thermodynamics. The naming of this law might seem odd at first, as it was formulated after the first law of thermodynamics. However, in a logical sequence, it precedes it, hence the name zeroth law. This fundamental law states that if we have two bodies, let's call them B and C, that are each in a thermal equilibrium with a third body, A, then B and C are also in thermal equilibrium with each other. This zeroth law not only defines properties of temperature, but essentially also establishes that temperature is a state function. This is a crucial point. Without such a definition, we'd be in chaos. If the temperature depended not on the current state but on some arbitrary other processes, there would be no thermodynamics as natural science. Now, having covered our basic definitions, we can discuss the scope of classical thermodynamics. It's important to understand that thermodynamics only considers equilibrium states. From a thermodynamic perspective, in classical thermodynamics, we cannot make statements about a state that isn't in equilibrium. Another critical point is that classical thermodynamics examines matters such as the relationships between the state functions of a system, the heat added or removed, and the work done. It does not concern itself with the microscopic composition of the system. The reason for this is straightforward. If one is familiar with the development of thermodynamics, the microscopic composition of substances or matter was not known at its inception. For instance, Carnot, in his work, employed the concept of phlogiston. It is an obsolete concept of heat as a liquid. He utilized this concept, formulated his principles, and we can still apply them now. For us, it doesn't matter if we talk about phlogiston or molecular motion. Only much later, after the development of classical thermodynamics, did the focus shift to the microscopic composition of systems, leading to statistical thermodynamics and kinetic gas theory. This characteristic is a strength of thermodynamics. We don't need to know about the composition of the system. It is not the composition of the system that is essential for thermodynamics. We have these foundational laws, the laws of thermodynamics. Regardless of whether we have phlogiston or molecular movement, the laws of thermodynamics remain consistent. This consistency is an advantage, highlighting the power of thermodynamics. As we have just mentioned, thermodynamics operates within the bounds of equilibrium. Yet the idea of a reversible process emerges within this framework. How are the concepts of unchanging equilibrium and the change of state reconciled with each other? Imagine a transition from one state to another. This state change must be caused by an external driving force, such as pressure or temperature differences. If we reverse this force even slightly, technically by an infinitesimal amount, a reversible process will move in the opposite direction. This is how the concept of a reversible process is often introduced in textbooks. A simpler way to understand it is to say that during a reversible thermodynamic process, the system is always in equilibrium with its surroundings. In general, there is a very close relationship between reversibility and equilibrium. Consider a gas held inside a container equipped with a moving piston. If the external pressure, denoted as Px, equals the pressure of the gas, or internal pressure Pin, the system locks itself in mechanical equilibrium with the surroundings. Even though the piston can move, opposing forces balance it out, keeping it stationary. This equilibrium means no energy transfer as work occurs between the system and the surroundings. However, an infinitesimal variation in external pressure alters the gas volume. A minuscule decrease in the external pressure causes the gas to expand slightly, and a minuscule increase in the external pressure causes the gas to slightly contract. According to our definition, such behavior designates a reversible process. On the other hand, if the external pressure, for example, significantly surpasses the internal one, a small reduction of Px won't reverse the process's direction. Such a system is not in mechanical equilibrium with its surroundings, and the compression that we observe is a thermodynamically irreversible process. In practical terms, for reversibility to manifest, the establishment of equilibrium within the system must also occur much faster than any change in external parameters. The system must rapidly adjust to new external conditions. If we slightly move the piston, the gas molecules will quickly rearrange themselves, adopting a new configuration and re-establishing an equilibrium with the surroundings. While a truly reversible process might be not entirely achievable, it remains an important fundamental concept in thermodynamics. Approaching this ideal becomes feasible when processes ensure a rapid establishment of internal equilibrium in the face of external changes.